Okay, so let's start on the next page here. Let's talk about some um, terminology, and we can relate it a little bit to our heads and tails situation that we were doing. Okay, so real important. We're going to talk about probability experiments. So the probability experiment that we just did is we flipped two coins at the same time. Wow, right? Okay. So what is a probability experiment? It's an action or a trial through which specific results, counts, measurements are obtained. So you flip the two coins, you record your result. You flip the two coins, you record your result. Okay. So we're getting information from each trial of the experiment. Okay. So an outcome is a result of a single trial. Somebody give me a result from the experiment that we did. Heads is a result, isn't it? So that's an outcome, or heads tails, whatever, right? How many outcomes were there? There was actually really four, because remember we said that this would be a different outcome than this, because I'm saying that the first one is the first flip and the second one is the second flip. So there's four outcomes, right? Just get used to those terms, okay? Okay, the sample space is the set of all possible outcomes of the experiment. So this would be our sample space from flipping the coin twice, right? Now I'm going to maybe get ahead here a little bit. That when we're working with probabilities, we'll put a capital P on the outside and we'll put brackets. And the thing we're trying to calculate the probability of, we can write it on the inside. Okay, so that thing that we write on the inside, sometimes we're going to put it like a capital letter. Sometimes we'll write out what the event is that we're trying to calculate the probability of. Okay, so maybe one event would be what's the probability of getting two heads on the roll or the flip of the coins. Okay, but this guy here is an event. So an event consists of one or more outcomes. And the event must be like a subset of the sample space. So like, again, the event could be like, what's the probability of it coming up with one heads? Well, that's really more than one outcome, isn't it? Because that could be this outcome here, and that could be this outcome here, right? So another little quick little experiment. Let's look at a different experiment, rolling a die. Okay, give me an outcome.
Two.
Is that the only outcome?
No.
Nope. What would the sample space be? It would be, right, all the possible outcomes. You could roll a 2, a 1, a 4, a 3, 5, and a 6, right? So that's your sample space. Sometimes the sample space is going to be really complicated. Okay? In this case, the sample space is really simple. There's only 3 or 6 different events. Okay? Give me an event in words that wouldn't just be a one number outcome. Well, we're only rolling it once. No, we're only flipping it once. We're only rolling the die once. But give me something that would have more than one outcome.
Is a 1 and a 3 and a 5.
Right, so odds. That's what I'm saying. What's the chance that the number is odd? So that is not a simple one thing event. It's a couple things. Right? So what's the probability that you roll an odd? Well, it's not and it goes on the next page and talks about it, and it's not a real big deal. But see, a simple event, a 1 or a 2, is different than a non-simple event where odd. See, being odd is a non-simple event. Simple event is 3. There's only one of them. Okay. To the last problem. Okay, so let's do this. This is important. Have you ever heard of this? Tree diagram in probability? Okay, maybe not. Okay. What we're going to do is we're going to simulate. I'm going to call flipping a coin as event A. I'm going to call rolling a 6-sided die as event B. So what I want you to do is I want you to put a dot. And I'm going to put an A there, and I want you to write I want you to make with a branch. How many options are there for event A? There is 2, so draw 2 branches. And write the result, write the outcome of the event at the end of the branches. Now put option B now. So now we're going to do event B. So we might flip it heads, and then we might able to do event B, which would be how many outcomes? 6. So draw 6 branches. And then draw the outcome of each of those. But also remember that you could have rolled or flipped a tail and then got the 1, 2, 3, 4, 5, or 6. So you got to draw your 6 branches off of there as well. So that would be a tree diagram that would represent doing one thing followed by the other thing. Okay. So I'm going to make up something else. I'm going to make something that I'm going to call it event A, flip a coin, event B, flip a coin, event C, flip a coin. So we're flipping 3 coins. So the first event, 2 options. The second event, 2 options off of each of the first. And now draw 2 more branches off of each of the 4 spaces at the end here. I'm running out of space. And then we're going to go back and we're going to talk about these, but that would be a tree diagram with either 2 consecutive events or 3 consecutive events. So you could do it 4 or 5 or 6 or whatever. So the next page is going to kind of talk about something that we just did, and we'll maybe refer back to it. All right. If one event can occur in m ways and a second event can occur in n ways, then the number of ways that the 2 events can occur in sequence is what? Well, let's look back here. How many ways could you do this event? 2. How many ways here? 6. Well, how many ways could you flip the coin and roll the dice?
12.
There's 12. There's 12 ending branches here, right? And we could even list the sample space here, because this is really what it is a way of listing the sample space. H1, H2, H3, H4, 5, 6, and then the other 6. So there's 12 things in our sample space, so there's 12 ways of doing this if you take the number of ways of doing the first one times the second one. So multiplication, right? How about here? How many ways of doing this? Flipping 3 coins. 2 times 2 is 8. How many branches do we have here? 1, 2, 3, 4, 5, 6, 7, 8. So you multiply the number of ways of doing one event times the number of ways of doing the next event. And again, it can be extended to any number of events, not just 2 in a row or 3 in a row. So why is it important to count how many ways you can do something? Maybe, but you're going to use that to calculate some probabilities, because you have to count how many ways you can do it. That will help you count the number or the probability of that event.
Can you just add up the end, like all the where the branches end?
Yep.
Yeah.
So let me ask you this. Okay, I'm gonna randomly pick a first digit to put on my license plate. It's gotta be a number. How many ways? There's 10 digits. And then the second place, or the second thing could have 10 digits.
Yeah.
So I have 100 times the third one, 1,000. You don't wanna have to draw those.
Yeah.
So the simple ones you can draw, but the complicated ones, maybe you wanna just multiply it so you can think in your head how many ways are there doing it.
Okay.
And we'll talk more about that, but that's why you wouldn't want to always draw it. Okay. These are just pictures of tree diagrams in your book. We don't need to look at that. Okay, so now we're gonna kind of relate what we did at the beginning of the period with heads and tails to some different ways of calculating the probability of it. Okay. So the first way that we're going to calculate probability is through classical or theoretical methods. So let's say that we wanted to calculate the probability of it coming up heads once. So our event E is this. Well, what are we going to do? We are going to count the number of outcomes in the sample space, which in our example was 4. And then we're going to put in the top the number of ways that event E could occur, the number of outcomes of event E. And what's the number of outcomes where it comes up heads one time in these 4? There's 2, so your probability of it coming up heads once in a 2-coin flip is going to be 1/2, 2/4. That's theoretical, right? Okay, so let's do this. Our probability experiment now is just going to be rolling the die. Okay, so what's the probability of event A? 1 out of 6. What's the probability of event B? 0, right? None. 0 out of 6. Not going to happen. Chances of it being 100 degrees in Mandan, North Dakota today is 0.
I would say
0.
It's 1 degree right now.
It is 0. I'm going to go out on the limb and say 0. You don't want to say 0 too often, but I'm going to say 0.
Here's a what if the sun gets super close somehow?
No.
What if the Earth gets hit right now and we get moved close to the sun?
Okay, so I'm going to go 0.0000000000001. All right. Okay, how about rolling a number less than 5?
Well, 1 out of 5.
4 out of 6. Now, one thing we haven't talked about is how can you leave probabilities? You can leave it as a fraction, you can leave it as a percentage, you can leave it as a decimal. Could you simplify that fraction? Absolutely. Right? So rolling less than a 5 is going to be a 4, a 3, a 2, or a 1. So there's 4 ways out of the 6, right? So this is all theoretical probability. So now let's talk about empirical or statistical probability. So let's do this. Let me write down a problem. So that's the probability of getting heads come up one time. Statistically, well, what are we going to do? We're going to count the frequency of event E. How many times did it come up heads? Once. Well, in our results, it was 71 times.
No.
Or, yeah, 71, isn't it?
It was
143.
Okay, I'm sorry, 143. And then we ran a simulation of, so that's 173 it was? No, 143 over 270, and we got that to be about 53%. Okay. Now, I guess I didn't put there that the total number of outcomes of the experiment or the frequency was going to be your denominator. Why aren't they the same? Well, because it's theory and practice. Theory and practice aren't always going to match. Here's the link between the two, though. Here's the link between experiment or theoretical probability and experimental probability. The law of large numbers says as an experiment is repeated over and over and over again. So we repeated it 270 times, but maybe we could do it more and more and more. And as we repeat it over and over and over again, that empirical probability, statistical probability, is going to approach what?
Zero.
No. The other one, what's the other one called? Theoretical. That's the law of large numbers. The more and more that you do this, the closer your statistical probabilities are going to get to the theoretical probabilities. So, one thing that we will do a lot in here is we will talk about cards, we'll talk about dice. I'm not promoting gambling, okay? The truth is that probability really came about by people that knew more about the chances of games than other people, and they were able to win money, okay? So I don't promote it. In fact, I was at a casino for 2 days this weekend at a football conference, and I didn't spend a dime. I am telling you not, and I've got it on tape that I'm saying that I am not. Okay? But we are going to experiment with some things, and I'm going to show you another game that we're going to do. And it's Skunk. Some of you have played Skunk before. Some of you hadn't. Well, I'm going to show you how to play it. Okay, so I want you to write Skunk on a piece of paper somewhere. I want you to write a 10 in the S column and stand up. Okay, so here's a skunk. A skunk, so you have 10 points because I rolled a 10, total of 10 points, okay? If you think that I'm going to roll a 1 on the next roll, sit down. It could be a 1 on the left, a 1 on the right, or a 1 in both. All right, everybody's up. If I roll a 1, you lose your points.
All of them?
Yep,
Alright.
in that column,
Alright.
which is only 10 right now. Everybody lost their points. Write a 0 down. Write down the number 8 in the K column and stand up. And we do it again. If you think I'm going to roll a 1, sit down. Now you get 9 more points. So now you have 17. Now once you sit down, you have to stay seated in this column. Okay, so you can stay up if you want. If you think I'm going to roll a 1, then sit down. Write a 0 down. Okay, put a total of 9 points under the U column. If you think I'm going to roll a 1, sit down. Cutter, you sitting down? Yep. Okay, everybody, they want to get on the board, right?
There we go.
Good move. Okay, put a 7 in the N column. If you think I'm going to roll a 1, sit down. So now write a 7, and now you have a total of 14. Think I'm going to roll a 1, sit down. You got to stay seated though.
Oh, is it still the end?
Just
column?
until for this column, right? Yep. 11. Total of 25.
Beat him now.
5 more. I think it's gonna roll 1 here.
Me too, but I need the points to beat them, so.
You got another column left.
Oh no.
Alright, now let's go.
Okay, we gotta see what it's gonna be,
We
right?
have way less points than us now.
True.
Okay, we'll see what it is.
Oh.
Perfect play. Okay, let's go to the K column, last column. Put a total of, get those skunks out of the way, 6. Okay, so who was like the most conservative? You had a bunch early. You had some early. So you guys got to play against them now because you know that they have some points.
Wait, so
You want to
It's going to be the total of each of the columns.
okay.
So you're going to add up the S column, K column. You're going to add them up at
So
the
we
end.
have in the end column we won't lose.
No. After you done.
We have to go one more.
Oh no.
Total them up. Winner gets a prize.
I have 39. She also has 39. Yeah, I think he has 39 also.
37.
How much did you have?
25.
Okay, come up and get a candy.
Oh wait, it's 10 and 9. 9 plus 25.
34. Okay, so let's do this. Now, let's do this. Calculate this for me. Let's calculate the probability of a skunk. So how many ways are there of doing event A? Rolling the first die.
So,
And then the second die. 6. So how many ways are there of doing the first die and the second die? 36. 6 times 6, right? And so here they are, right? 6, 6, 6. And these are the sums. But how many skunks? Would this be a skunk?
Yeah.
Yep. This one? Yep, because of the 1 skunk.
Yeah.
So there is a total of 6 skunks so far. 7, 8, 9, 10, 11. So the probability of getting a skunk is almost a third. Just a little bit less than a third. Okay? So let's play it one more time. Let's do this. One more thing is, what would be the probability of getting a sum of 2, 1 out of 36? What's the chances of getting a 7?
1 on 36.
How many 7s are there here?
6.
6 out of 36, right? So do this for me. Write down the probabilities of getting each of these sums. So the most frequent roll is getting a sum of 7, right? It's a lot more common than getting a sum of 2. 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. And I didn't put the 36 here, but it's out of 36, right?
That why 7's like a lucky number.
Yeah, 7 is a much more common roll on 2 dice. Okay, let's play again. Put a 10 under your S column and stand up. Or sit down if you think I'm going to roll a 1. I'll wait. You up, Elise, or are you down? She got 11. She got 10 points in the bank. She got 10 points in the bank. 10 points in the bank. Okay, put an 11 in the K column. What are you confused about?
I don't even know what I'm confused about. That's how
I gonna roll a 1? Yep. So you have 0 points in that column. Where are we at? The U now?
Yeah.
Okay, put a 6 on the U. She's up.
And 1.
Everybody has 0 except for Cutter. Last column. Put no end column. Sorry, put an 8 in the end column.
She got 10 points. I got 3.
Did you break this?
Just
Look, Carter, you
Yeah.
sat for that 10 too?
Yep.
You sitting this whole time?
I stood up for the K.
okay, here goes. You're locked in. You gotta stay standing.
So you only play on if there's no one?
If you're sitting, you don't get those points.
But if you sit and there's a one,
Then you get the points that you had when you sat down.
but then you don't roll again for that column?
Yeah, because it's a skunk. Everybody's done. Okay, here goes. 10 more.
Oh no.
I play Caden.
Okay, we gotta see what it is, right?
Yeah. There's no way I would have stayed for that long.
Okay, last column. Put a 8 and then stand up.
Caden has the Okay, how much is that last one worth? You have 80?
Okay, here we go. You guys are locked in. You down?
Yeah. I'll sit.
Bad choice.
No.
Okay, I want points.
Total them up.
At 56. 45.
56, you said?
Yes.
Anybody beat 56?
140.
Okay, get a treat. Okay, so the lesson, that assignment, I've got one more thing that I could talk about. You could do a lot of those, and you could start it on them. I'll finish tomorrow with the lesson.